But we will start with a very important topic. The talk is about the advantages that quantum resources can provide when used in classical information processing. I think this is a very important. I think we should, we should know about when we in the design of a quantum programming language since the very first phases of the process of construction of a language, because it is important to keep in mind the very essence, quantum essence of a programming language, and try to incorporate already at the abstract level, the first phases of the construction, this the real source of quantum speedups, computational speedups. And it is an honor and a pleasure to have Samson Abramsky talking about this and explaining to us how the theory of quantum monads can describe this resource in the search of a quantum advantage. So thank you for accepting our invitation, Samson, and we are all ears.
Is it working? It is working. Oh yeah, I can hear something. Great. Okay, well, thanks very much, Alessandra, and thanks to all the organizers for this invitation. As I pointed out when I was very happy to receive the invitation, and it's a pleasure to participate. I haven't directly been working on quantum software, but I hope that this topic that I'll be talking about is at least suggestive of ideas, longer-term ideas that may eventually be incorporated in quantum software. So I'd like to talk about the quantum monad as a means for encapsulating quantum advantage. After all, the reason for building quantum computers and for writing and using quantum software is to exploit the fact that with use of quantum resources, we can achieve effect that we can't achieve just by classical computation. So, but the other word, significant word apart from quantum in the title is monad. So just a word on that. That is something that should be familiar to programming language researchers. It's worth pausing for a moment to remember that monads are actually a fundamental mathematical structure arising in category theory, universal algebra, topology, and so on, which has turned out to be a very fundamental concept for programming languages. It was first introduced into the programming world by Eugenio Moggi in the semantics of programming languages, but then it was incorporated as a major feature of the Haskell programming language and has been very influential since then. So we find monads in Python, and although I'm no expert in Rust, I understand that monads also appear there, and it's quite a widespread idea by now. And we also find it in quantum programming languages such as Quipper. So monads are used to encapsulate effects, particularly in functional programming languages. And just to sort of briefly recap how a monad looks, if we think of a functional program as some kind of, so we have some kind of functional program F, which has an input type A and produces an output type B. The idea of a monad is that it modifies the type of the output, in particular in the way it's usually used, giving rise to so-called Kleisli morphisms. So not just things that go from A to B, but from A to M of B, where M is the monad. And this extends the type B by allowing for various effects that can be added into the language. And in our case, we'll be interested in effects that involve using quantum resources. There's also a unit of the monad which embeds values into effects. And there's the very important idea of Kleisli extension. If I have such a map from A to M of B, then applying this dagger operation, I get a map from M of A to M of B. So I can extend the input to be not just the values in A, but also these effects that can surround A in some sense. And this is very important because without this, we wouldn't be able to compose these maps. The trouble with A to M of B is it's asymmetric, and it's not at all obvious how you can compose things, which is the fundamental thing in the whole of programming, that you can you have compositionality. So with this Kleisli extension, if I have Kleisli maps from A to M of B and from B to M of C, by applying this Kleisli extension, I can reconcile the type of G with the type of F by applying the dagger to G, and then simply compose them to get another Kleisli map from A to M of C. So this is the Kleisli composition. So if you've used Haskell or any of the other languages I mentioned, this should be familiar to you. Of course, there's more mathematical structure underlying this, but this is what one sees at the programming language level. And to take one of the most basic examples, the maybe monad, which simply adjoins to a set or a type one extra element. So plus is meant to be disjoint union here, and this encodes a notion of partiality. So a Kleisli map from X to maybe of Y will take an input in X and either produce an output in Y, or maybe it doesn't, and that's captured by it going into this additional value that we've adjoined. And then it becomes a sort of exercise you can do while you read to work out what the unit map is and what the Kleisli extension is. So the Kleisli extension, if it gets a sort of undefined value in its input, will simply pass this over to the output. Okay, so that's monads. Now, what we want to do now is to show how some of the fundamental ideas that enter in discussions of quantum advantage, the foundational level, can be packaged as a quantum monad in quite a general setting of relational structures. Graphs you can think of as a specific, particularly important example, which gives a high-level structured approach to encapsulating quantum resources. And I'm going to present this as a mathematical construction, but the idea is, or the hope is, that it can, or one hope is that it can provide the basis for developing high-level quantum programming features. And I'll come back to this at the end. Okay, so let's begin with the classical information processing paradigm we're talking about, which is homomorphisms of relational structures. So, I mean, a relational structure is just a sort of generalization of the idea of a graph. It's a set with a bunch of relations given from a particular signature. Each relation has an arity. So the most basic case of a graph would be a set with a single binary relation. That would be a directed graph. If we make a couple of assumptions, like the relation is symmetric and irreflexive, then it becomes a simple graph. And then a homomorphism is just what you'd think it would be. It's a function on the underlying sets which takes tuples in each input relation to tuples in the relation on the output structure. So it preserves the relations which are part of the structure. So again, the canonical example would be graph homomorphisms. Now, these notions are absolutely pervasive, firstly in logic, also in logic in computer science, but in computer science itself. Relational databases are all about these kind of structures. Constraint satisfaction is exactly expressed in terms of, can be expressed in terms of homomorphisms of relational structures. Finite model theory and descriptive complexity are all about these things. It is also important in combinatorics as well. So these are very pervasive notions, and what we can ask is the question, what would it mean to quantize these fundamental structures? So here's the sort of paradigm I want to discuss of non-local games. So I guess everyone has, well, probably everyone has seen some version of this, but just to it's a game or computer science flavored way of looking at Bell experiments is one way of looking at it. But we can just thinking of it as a game, the idea is Alice and Bob are playing and they're meant to cooperate, but we don't allow them to have any classical communication between themselves while the game is being played. And there's a verifier who sends inputs to Alice and Bob, and they have to produce suitable outputs which meet some condition that we've imposed, some winning condition. So in particular, we can consider a homomorphism game, which is played on these finite structures. And the idea is that Alice and Bob have to cooperate to convince a verifier that there is a homomorphism from A to B. By the way, I mean, again, if you want to think of a concrete example, think of graphs. A graph coloring, let's say a 3 coloring of a graph, is exactly a homomorphism from the graph into the 3-element clique, the 3-element complete graph. So convincing the verifier that such a homomorphism exists means convincing him that there is a 3 coloring of the graph. So a very standard computational problem, just as an example to keep hold of. Okay, well, in the way we play this game, Alice and Bob are separated and not allowed to communicate. We sort of put them in separate rooms, take away their mobile phones, put the Faraday cages on. Of course, if we want to go to the extreme, they're space-like separated in different kind of spaceships. There isn't enough time for them to communicate because of the boundedness of the speed of light and so on and so forth. Anyway, they can't communicate. And in a play of the game, the verifier sends Alice an index and a tuple. It says, I'm giving you a tuple from this relation, and it gives Bob an element of the set. Alice returns an output tuple corresponding to her input tuple, and Bob returns an output element corresponding to his input element. And the winning condition is that Alice and Bob win that play. Firstly, the output tuple that Alice sends has to be indeed in the output relation. And secondly, there has to be a consistency between Alice and Bob. If Bob's input element equals the ith element of Alice's input tuple, then Bob's output has to be the ith element of of Alice's output tuple. So they have to be consistent, but that's the sense in which they have to coordinate or to have correlated behaviors in order to win the game. Now, they can, use probabilistic means, throw dice or whatever, but what we're interested in here are perfect strategies, which is one in which they win with probability 1. Now, in the classical setting, with these constraints that Alice and Bob can't communicate during the game, then it's easy to see that the only way they can always win is if there really is a homomorphism from A to B, which they've agreed on in advance, and they simply play according to what the homomorphism tells us. But if we allow quantum resources, the situation changes rather radically. So how would we play the homomorphism game with quantum resources? So now we consider there are finite, there are Hilbert spaces, which we're going to think of as in a tensor product. So Alice can access H and Bob can access K. Alice can only perform operations on H and Bob only on K. So they're localized in that sense. And then corresponding to each question that the verifier might ask Alice, she has a quantum measurement, a POVM, whose outputs lie in the possible output tuples of the output structure. And similarly, for each input that Bob can get, he has a quantum measurement, a POVM, with the outcomes lying in the possible values of the output structure. And how do they use these resources? When Alice gets her input, she measures, she performs the corresponding measurement on her part of the state. And similarly, if he's given his input, Bob performs his corresponding measurement on his part of the state. These parts are separate, but of course the state may be entangled, and in cases of interest will be entangled. And anyway, they obtain this joint outcome, with the probability given in the usual way by what you will recognize as the Born rule. I haven't used Dirac notation here, but it's just the usual formula for computing the probability of performing a quantum measurement in a given state. So now we say that if with probability 1 the outcome satisfies the winning condition, then this is a quantum perfect strategy. And we can write the winning conditions explicitly in terms of the quantum operations. So remember what the winning conditions were. We have to get an output tuple correctly in the corresponding relation of the output structure, and there has to be this agreement between Alice and Bob. And that translates into, so what we're saying is we never get the wrong outcome. We never get something that violates those conditions. And we can express that in terms of these two conditions, that we get a probability of 0 of ever doing something that violates the conditions. So we always get a positive, so whenever we get a positive probability, we've satisfied the conditions. So this strategy always wins. Okay, so what would be an example of this? Well, we can use a familiar example, well, familiar to many, of the Mermin or Perez-Mermin magic square. Now, how does this look? We have a bunch of variables which we arrange like this, 9 variables, and the values we can observe from these variables are 0 or 1. And we require that each row and the first 2 columns have even parity, and the final column has odd parity. And if we write that down as some equations over Z2, we're saying, so we think of it as Boolean variables, and we just use exclusive OR. We're saying if we take the exclusive OR in the rows and the first 2 columns, we get 0. That's a way of saying we get even parity. And in the final column, we get 1. So a system of 6 equations. And it's very easy to see that these equations cannot be satisfied classically. There's no way at all we could set values in Z2, 0 or 1, to these variables which would satisfy these equations. The simplest way to see that is sum all the left-hand sides, and you see that every variable occurs twice, so it must cancel in Z2 using addition mod 2 or exclusive OR. And if we sum the right-hand side, we get 1. So we're being asked to solve the equation 0 equals 1, which we can't do. Now, famously, we can define appropriate quantum measurements just using 2-qubit Paulis, which will meet these conditions. Firstly, on each row and column, so I'm writing here, for example, xi to mean Pauli measurement x in the first qubit and the identity in the second qubit, and so on. So you can easily see that if the elements lying along each row and column pairwise commute, so they're valid things to measure together, and also they satisfy exactly the conditions we've given. If we multiply out the rows and the first 2 columns, we get the identity, and if we multiply the last column, we get minus the identity because of the nature of these spin operators. So that would be an example where we can get a perfect quantum strategy where no classical strategy exists at all. And we can sort of generally talk about Alice-Bob games for binary constraint systems. Same kind of idea as we've just seen. Alice and Bob, in fact, is essentially the same as the homomorphism game that we've already considered. Verifier sends an equation to Alice and a variable to Bob, and the winning condition in these terms is that Alice returns a satisfying assignment for the equation, and Bob returns a value for the variable consistent with Alice's assignment. If you're familiar with these things, this is really a way of putting in the no signaling condition. And the perfect strategy is one that wins with probability 1. So there's no classical strategy, but Mermin's construction shows there's a quantum perfect strategy. So the first thing we're going to do is take all this machinery of strategies for non-local games and showed that it reduces to a much simpler form, which is exactly the idea of what we'll call a quantum homomorphism. And that will let us define the quantum monad. So here's the sort of, I don't want to go too much into technical details, but it all looked quite general. I mean, we're given some general state. Actually, you can see for perfect strategies, we might just as well use a perfect state as a mixed state, sorry, a pure state as a mixed state, but it seemed all very general, POVMs, an arbitrary state, and so on and so forth. But actually, the existence of a quantum perfect strategy implies a normal form that drastically cuts down the possibilities. If we're going to have a perfect strategy at all, the state can be taken to be very specifically a maximally entangled state. The POVMs can be taken to be projective, and the measurements used by Alice and Bob sort of turn out to be directly related. And by the way, this is not a matter of going from POVMs to projective measurements by dilation, because we're actually reducing the dimension when we perform these transformations. It's a different thing on a technical note. But anyway, the interesting point, I don't want to get into the technicalities, but what this result shows is that all the information determining the strategy is in Alice's operators. Moreover, Alice's operators must be chosen non-contextually, so that the measurement chosen for input x is independent of the context x. And this means that we can define specific projectors just corresponding to the input-output relations, tuples that we're interested in. So we get a drastic simplification of the very complicated-looking formalism of non-local games into this notion of quantum homomorphism. By the way, I mean, although this is a sort of mathematical result, we can at least imagine that this is a kind of compilation that's going on. Or possibly, I mean, possibly we would compile in the opposite direction, but at any rate, we're relating to quite different looking setups. So what is a quantum homomorphism? This is going to look a lot simpler because we've now forget all about Alice and Bob, we forget about the state, and we're just talking about a kind of relation, indeed, between the two structures that we're given. But the relation takes not sort of truth values, not a Boolean relation, but it's valued in projectors. This is the quantum element of it. This is where the quantum resources come in. So we get a family of projectors indexed by the elements of the input structure and the output structure. And the first condition says, for fixing each input, this is going to give us a resolution of the identity. So it's going to be a well-defined quantum measurement on the outcomes. So the outcomes will correspond to the possible outputs that we might give given a certain input from the input structure. And then we get some commutation conditions, which are quite important, because given that we need to know that projectors commute in order to be able to form a joint measurement, which is what allows us to express this correctness condition, that we assign, in any case where we assign a non-zero value, a non-zero projector, to an input-output relation, then indeed we have a valid homomorphism. So for a given input tuple in a relation, the output tuples that have non-zero projectors associated with them, non-zero quantum possibilities of being produced as output, must themselves be in the relation. So if you take that contrapositively, then we get this condition here. So we can write the existence of a quantum homomorphism in this way with this arrow Q. And then what we have, by virtue of the sort of this reduction of structure that we just saw in the previous slide, is that to have a quantum homomorphism is exactly equivalent to having a quantum perfect strategy for the homomorphism game from A to B. So we started off with this complicated operational scenario of a non-local game where we try and convince the verifier that we have a homomorphism, and we end up with this more structural idea where most of that structure is gone, and we just get these projector-valued relations. And now we can take one further step, which is what gives us the quantum monad. And the beauty of this is that this will be, we will modify the structure, but the morphisms will now be ordinary classical morphisms of relational structures. So to be a quantum homomorphism from A to B, which as we've just seen corresponds to having this winning strategy for the quantum strategy for the homomorphism game, is going to be exactly the same as having a classical homomorphism from the input structure A to this modified type, not B, but this quantum monad of B. So this is the idea of the quantum monad. So it modifies the type in the same way that any monad modifies the type, as we were recalling earlier, like the maybe monad and so on. So quantum homomorphisms from A to B correspond bijectively to classical homomorphisms from A to Q of B. Now there's one extra little point here which is quite important. It isn't just Q, it's Q sub D. This isn't just a monad, this is a refinement of the notion of monad, which has become increasingly widely used recently, the so-called notion of a graded monad, where we use some indexing of resources to grade the level of the monad that we're using. And in our case, this D is the dimension of the Hilbert space that we're working with. So it really is allowing us to keep an accounting quite accurately of how much of the quantum resource that we're using, how many qubits we need, if you like. So quantum homomorphisms are exactly Kleisli morphisms for this monad. And this gives, I think, an elegant mathematical formulation of quantization for a very broad range of computational tasks. And to give one example, coming back to graphs, as we mentioned, having a coloring, for example, a 3-coloring or a 4-coloring of a graph classically corresponds to the existence of a graph homomorphism from the graph into the complete graph on 4 elements or whatever the number of colors is. And there's a notion of quantum graph coloring where we have where we ask for a quantum homomorphism of that kind. And this has been studied in some depth, and we know that quantum colorings can exist where classic or lower values of colorability, quantum colorability, exist in general than exist in the classical case. So these are very special cases of what we're describing here. And there are many other graph invariants where something similar happens. Okay, well, I don't want to go too much into the details and be too technically heavy, but I mean, just want to give an impression of what this construction looks like. It essentially is taking the, well, okay, let's have a look at it. So we're given an ordinary relational structure A. We can think of it as a graph. And we're going to build this new structure, modifying the type to make this QD of A. So D is fixing the dimension of the Hilbert space that we're working over. And the universe of this structure, so remember we're going to have, so we had a set of vertices and an edge relation, if you like. We're going to have a new universe of the structure and a new relation. So the universe is going to be the set of all functions from the old set into projectors on the d-dimensional Hilbert space, which satisfy this normalization condition. So it's really like a distribution or projection valued measure on the structure. You know, we think of probability distributions valued with reals in the unit interval, and this is projector valued distributions. And then for each, so we can think of them, if you like, as quantum truth values. And then for each relation, so that's just defining what the new universe, the vertices or whatever of the structure are. And we have to define also the relations on the structure. And these are going to be the set of tuples. They're now going to be tuples of these projector valued distributions, which again satisfy similar conditions to those we were just seeing. So we have something that corresponds to the fact that we can never get a tuple that takes us out of the relation that we started off with. And in order to say that, we have to jointly apply, jointly form the product of these projectors And in order to do that, we need these commutation conditions. So this is saying that pi of x and pj of x prime commute for all choices of I and j. Okay, so the commutation conditions are a necessity for this to make sense. And again, the sort of basic thing that tells us what's going on is that the quantum homomorphisms that we've already described, there's a bijective correspondence between those quantum homomorphisms and the standard homomorphisms, ordinary classical homomorphisms, but into this quantum monad on B. And again, to remember, this relates us to the non-local games, which we started off with, which is one of the fundamental ways of talking about quantum advantage. Okay, so as we've said, the quantum monad is graded by the dimension of the Hilbert space. And to see how this comes into operation in an interesting way, I've still got my Kleisli composition. So if I got A to QD of B and B to QD prime of C, I need to glue them together to get a new map from A to Q of something C, and it's going to be the product of the two dimensions. And this is not so surprising, because if you think about, if we go back for a moment to the non-local games where we had Alice and Bob living on the tensor product and applying their local measurements, that underlying idea is still here, because of course if you have a d-dimensional Hilbert space and a d-prime dimensional Hilbert space, the dimension of their tensor product is d times d prime. And that's what's going on here. We need to have enough room for both sets of players to play, as it were. So we get that by taking the tensor product of the quantum resources that they're using. So we can sort of operationalize this again in terms of how we would actually perform the non-local games that would underpin these quantum homomorphisms. And the actual formula is a sort of version of relational composition, in a sense. We sort of sum over the thing in the middle, the thing that comes from the B structure there, but the product here is the tensor product. So the issues with possible non-commutativity don't arise. Yeah, I could show you some more complicated looking formulas, but I think this will suffice. So another way of looking at it in terms of quantum homomorphisms is this thing, which looks even more explicitly like a relational composition. So remember, if you compose relations, we're saying it's a sort of, R composed with a relational product of R and S relates X to Z if for some Y in the middle, so that's a summation of something in the middle, R relates X and Y and S relates Y and Z. And that and is this tensor product over here. But it's important that it's the tensor product and not the product of projectors, which in general has no reason to be defined. Product of projectors is only defined to give us a projector when the projectors commute. That's why these commutation conditions come in at various crucial points. Okay, so now having set this up, I'd like to, another nice point. We started with non-local games. We ended up through quantum homomorphisms to the quantum monad. Now we're going to relate this back to contextuality, a favorite topic of mine, which is also intimately related to quantum advantage. The first point is, foundationally, contextuality is a, or maybe the, key form of quantum non-classicality. The only reason it's worth doing quantum computation, given that it's difficult and expensive, is that it lets us do things we can't do classically. If we're going to do things we can't do classically, it must be because of the non-classical features of quantum mechanics. But what are these? Well, one of the main things that has been found over the many decades of research is contextuality. Maybe it's the key one. It's important for quantum foundations, but also very much as a resource for quantum advantage. And there are many examples. Let me just mention a few. One of the very few unconditional separations of classical from quantum are in the striking results by Bravy, Gossett, and Koenig for shallow circuits. And the way that you sort of show that you can get a quantum shallow circuit which provably does better than any classical one of the same depth of shallow circuit is by starting from a contextuality construction, maybe a GHZ construction, or indeed a Perez-Mermin square, such as we saw earlier. And in a very nice generalization of this work by Sievert Osnes in his recent thesis with me was to show that you can start from any contextuality construction in a very broad class and produce systematically examples of shallow circuits with unconditional separation from classical shallow circuits. Another famous contribution, I mean the title says it all, by Howard et al., is Contextuality Supplies the Magic in Quantum Computation. This refers to a very important paradigm for actual quantum implementation of sort of quantum architecture is the where you sort of onto Clifford operations, the things that are tractable and nicely fault tolerant and so on. You have to get universality, you have to inject a magic state that lets you sort of augment the gates, the Clifford gates, with the T gate or whatever it is. And they show there that contextuality plays a key role in this magic state distillation. And one more example, another important paradigm is measurement-based quantum computation. And again, provably, contextuality is a key resource for quantum advantage in measurement-based quantum computing, with work by Robert Rausendorf and then by myself and some colleagues on that topic. And there are many more examples. But anyway, the main point is contextuality is very strongly related to quantum advantage. Now, the relation with the quantum monad is actually we can make a three-way equivalence between a particular form of contextuality, so-called state-independent strong contextuality arguments. If you're familiar with Koch and Specker theorem and related results, those are sort of exemplars of that. And in fact, Perez-Mermin is itself an exemplar of that. That's point one. Point two is quantum advantage in constraint satisfaction. And point three is existence of quantum but not classical homomorphisms between relational structures. So all these three, there are sort of systematic back and forth bijective correspondences between these things. So again, the quantum monad carrying quantum homomorphisms, it lets us account for a large swathe of the kind of constructions that give us quantum advantage in many situations. So I just want to, how much time do I have left actually? Is keeping me, Alessandra is far away, but, sorry? 10 minutes. Oh, then I think we're doing fine then. Great, thank you. So just, I don't want to sort of, again, go into too much detail, but just to say a little bit about contextuality in case it's not familiar. The essence of contextuality is that not all properties can be observed simultaneously. This is to do with the fact that, you know, projectors, or more generally quantum, observables don't commute, and they can't be formed into joint observables. Those things that can be formed into are jointly observable can provide a family of partial classical snapshots which overlap, and and this brings us back to the non-classicality. Contextuality arises where there's a family of data which is locally consistent but globally inconsistent. You have this family of these snapshots, they agree locally on overlaps, but there's no one thing out there which sort of results from gluing them all together. And you can think of this as why there's no classical solution, and yet there can be a quantum one. So there's sort of this, as a nice way of sort of visualizing this idea of local consistency and global inconsistency. Suppose we saw some structure in the distance and we took some snapshots of parts of it, and then we looked at these individually. Each of them looks okay. We can even see they're locally consistent because where they adjoin, they match up in a reasonable way. So a locally consistent family of data. So surely there must be something out there that accounts for all these snapshots that we see. If we put it all together, we get what you may recognize as the famous Escher ascending and descending staircase, a sort of visual paradox. It seems to be either always going up or always going down. Actually, this was suggested to Escher by Roger Penrose and his father, I believe, a long time ago. And it's actually even mathematically quite related to contextuality as it arises in quantum mechanics. Anyway, if we start formalizing this, then we find we're not so far away from constraint satisfaction and homomorphisms. Again, I don't want to belabor the details, but this is a general approach to formalizing these things, which covers a very wide range of things and has proved to be robust and can be developed in various ways in this form introduced with Adam Brandenburger quite some time ago. So we have a family of variables, if you like. We abstract the idea of which variables can be measured together into this set of contexts, so simply sets of variables that can be measured together, and then there are possible outcomes for each variable. And then what we call an empirical model, an observed table of data, which we either get from experiments or observations, or perhaps by theoretical prediction, is going to be a family of probability distributions, one for each context, which tells us the probability of getting each particular assignment of values or outcomes to each of the variables in the context. That's pretty general. And then the idea of local consistency is that if you take any pair of contexts and you marginalize to the variables that they have in common, you get the same distribution. So locally, everything looks consistent. They agree on their overlaps. This is a very important point about the quantum story. That's why you get the same projector or effect appearing in many different measurements and getting consistent outcomes according to the consistent statistics according to the predictions of quantum mechanics. So this is the local consistency. Whoops. The idea that you can glue it all together globally is that there's a single distribution on all the variables. So there's D, which is a distribution over possible outcomes for all the variables, which marginalizes to recover all the observable probabilities as we range over the context. So that's non-contextuality. And contextuality arises when such a global gluing together simply does not exist. This is the global inconsistency. Now, a particular form, which arises in many important cases of non-classicality and quantum advantage, and which harps back to the Cauchy-Specker theorem and other such result, is where the model is so contextual that even not only can you not reproduce the statistics, you can't even find one single way of gluing all the local data together which is consistent with the observed statistics. Not even one way of doing that. If you like, there's a manifest contradiction even in the structure of the measurements themselves. So you may recognize, this is the PR box where we haven't bothered to write the probabilities in. They're anyway uniquely determined by the no signaling condition. And here is, just hinting at the sort of rich structure of these things, here is a sort of bundled depiction of the PR box. So we have the variables here, we have a fiber above each of the variables with its possible values, and the edges here tell us which outcomes can co-occur possibly. So the things where you have ticks on the boxes. So you get correlated outcomes on 3 of the contexts and anti-correlated outcomes on the last of the contexts. By the way, it's this correlated, 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 anti-correlated also gives you the CHSH, the structure of the CHSH inequality. Anyway, in the case of the PR box, the contextuality, the inability to have a globally consistent description of the data is beautifully revealed here, because wherever you start, you never get back in one iteration to where you started. You have to go around twice. So that means there's no consistent way of assigning values to the variables, which is consistent with all the local information. So this is a sort of discrete Möbius strip. And it tells you immediately that this is an example of strong contextuality. Well, how can we get a quantum witness for strong contextuality? Well, again, we assign a state. To realize this sort of structure of data, we assign a state, and we interpret the measurements by various, whether we take PVMs or POVMs, then we can just compute the probabilities out using the Born rule in the usual way. And so indeed the Mermin magic square that we saw earlier and various Koch and Specker constructions provide examples of state-independent quantum witnesses for strong contextuality. State-independent means we don't even need to have a particular state and to compute out the probabilities. We just see from the structure of the measurements themselves that for any possible state, we'll never get any description that is consistent with the constraints enforced on us by these observables. And there are famous examples of just this. Okay. So again, we get a beautiful correspondence between these state-independent quantum witnesses and quantum homomorphisms. Essentially, the idea is that having this single consistent assignment that we need to avoid strong contextuality is exactly like getting a satisfying assignment for a constraint satisfaction problem. It's fairly clear when we put it in those terms. We're assigning values to particular values to all the variables that have to be consistent with all the constraints we pick up from looking at the different contexts. So the absence of such a thing classically means that there's no classical solution, and where nevertheless we can realize all that structure in a quantum way, then we get a quantum solution. So what we get is a one-to-one correspondence between state-independent quantum witnesses and quantum homomorphism. So again, we pick up all those examples from the literature of where we can demonstrate quantum advantage. An interesting point here, which comes back to the sort of the foundational topic, is that, I mean, the reason that Bell proved his theorem on non-locality, having previously, in fact, proved his own version of the Koch and Specker theorem, is he wanted a theorem with weaker assumptions, although the conclusion is also weaker, because he didn't want to rely, because he wanted to be able to rely on space-like separation and no signaling to support the assumptions, the hypotheses of the theorem. We can actually have your cake and eat it too. You can turn a state-independent contextuality proof into a Bell-type non-locality proof, essentially by putting in a state which just serves to a maximally entangled state, which serves to correlate Alice and Bob, and then playing this contextuality witness in both Alice and Bob. And essentially that's how, in the end, we relate these state-independent contextuality witnesses to quantum homomorphisms and then ultimately to non-local games. Okay, well, let me mention, so one of the things that seemed very appealing when we sort of introduced the quantum monad was that at about the same time, in some other work with Anuj Dawar and other colleagues, we introduced a structural way of talking about, again, about relational structures, but now with a view to classical finite model theory, descriptive complexity, constraint satisfaction, those things I was mentioning earlier on as why homomorphisms of relational structure already play a big role in classical computer science. So So we have this structural way of talking about that using so-called game comonads, where the kinds of games involved are things like bisimulation or Ehrenfeucht-Freysse games, games for comparing structures, where you one side tries to show the structures are the same, and the other, spoiler and duplicator, the other one tries sort of to show that they're different, and fooling the one who tries to show that they're different. It corresponds to showing that you preserve all the properties up to what you can express in a given logic. So it's a very rich paradigm that's been extensively developed in computer science. So the question that arose is, can we combine the quantum monad with game comonads to provide a basis for a quantum finite model theory and quantum descriptive complexity? So it's a very appealing prospect, but then actually doing it turned out to be difficult. Actually, there's a long-standing problem already going back to Moji's work with ordinary monads in programming languages. You may have 2 or 3 very nice monads, but how do you put them all together if you have many different features in your language? The sort of standard best way of doing that is with so-called distributive laws of monads, which let you glue them together. You need to push one past the other to get a workable Kleisli composition. And distributive laws may or may not exist, and actually quite often they don't. And you can equally have distributive laws between monads and comonads, and again, they may or may not exist. So in their recent theses, Nihal Shah and Amin Karamlou have made significant contributions of both negative and positive kinds. They showed that various cases that distributive laws don't exist. But Amin, in his very recent thesis earlier this year, has actually also got some very encouraging positive results, which go far enough where you can get combinations of game comonads and the quantum monad to develop quantum versions of spoiler duplicator games, and shows explicit quantum advantages possible in those games. If you're more familiar with bisimulation games, it's the same kind of thing, where you're comparing structures and showing that they're equivalent up to some level of observation. And you can find examples where you can win the game using quantum resources, using this combination of the quantum monad and game comonad that you can't do with classical resources. Okay, so just to finish up, I mean, there are, of course, various things that one would like to take further. I mean, we mainly talked about state-independent contextuality, but there's the whole world of state-dependent contextuality. We talked about perfect strategies, but it would be interesting to look at the non-perfect case and quantifying bounds on success probabilities. And since we have a well-developed theory of quantifying contextuality with measures such as the contextual fraction, that should be applicable here. But the main question I'd like to mention, and it's really a question which I find very interesting and brings us back to the actual theme of this workshop, is this is a sort of mathematical construction that which sort of comes from the sort of foundations of quantum advantage and so on. But can we bring it back and realize it in a quantum programming language? We know monads can be useful in programming languages. Can we embed the quantum monad and related structures into a quantum programming language? I think it may be possible to do that, but it's a non-trivial exercise. And the way I see it, I mean, at the moment, quantum programming languages, to a large extent, have high-level wrappers around low-level actual quantum features. So you just manipulate circuits and so on, the quantum level. We can see showing that something is a morphism in this quantum monad as a rather high-level statement about what that program is doing, which carries quite a lot of information with it. And I think we could imagine a sort of combination of formal verification, type theory, formal verification, and compilation, which would let us write code and eventually certify it as having this kind of type involving the quantum monad, which would then immediately prove something not just about that it's sort of faithfully representing a circuit, but that, you know, they're sort of sort of precise statements that can be made about the quantum advantage that's obtained by this program. So I think, to me, that's a sort of interesting line of possible research, and I hope may be of interest in stimulating future research in incorporating higher level features of quantum structures into future programming languages. So I'll just finish up by mentioning a sort of main reference on the quantum monad from a few years ago, a recent thesis by Amin, which I just mentioned as my co-authors, and thank you very much for your attention.
Thank you very much. So, are there questions to Samson? Yes.
Hi. Thanks for this wonderful talk. So, I want to ask a question about the standard CHSH non-local games is often posted in the symmetric version, but in your version that encodes the homomorphism game into the non-local games, actually here Alice and Bob are not symmetric. So I was wondering whether you can do it in the symmetric way, or whether there is some concerning for putting in the asymmetric case.
Yes, a very good question. You can do it in the symmetric way. It looks slightly more complicated, and in a way, I mean, I quite like this asymmetric way because it sort of points out that the thing of showing that you have a homomorphism is done on the Alice side. The thing that Bob is there to keep Alice honest, as it were, and you get this. So it's really no signaling condition. But you can do it in a symmetric way. That's one point. Another thing I should say is that there are several, when you go into the fine structure of it, there are several variants of these games. So there are synchronous versions, asynchronous versions, and so on. So you see there are some variations possible. I just gave a sort of basic format here for purposes of illustration.
Okay, so is it possible to translate the role of Alice and Bob into the programming language, or something related to the
one could imagine doing that,
yeah.
But in a sense, what we've described here is a different path where we can actually eliminate Alice and Bob. Maybe you could say that the interesting thing would be, so this is the path towards abstraction, where we reduce the structure in a slightly magical way, but there's no real magic in it, of course. You can find the details in both in these papers and earlier ones. But you could maybe see compilation as going in the other direction. So we start with a high-level specification, and then we introduce these operational features as the things, because in the end, to utilize the quantum resources, you would actually perform these local measurements on the in the Alice Bob game.
Yeah. Okay, thank you very much.
Okay, thank you.
All right, is there more questions? Yes.
Thank you. So the graded monad, if you perform measurements, you would somehow think that you would decrease the gradedness by collapsing the Hilbert space or something. Is that something that is reflected, or can be reflected?
Well, I see what you mean. The point is, when you're composing, if we go back to the, it's useful to go back to the. The point about the grading is that you need to describe these projector valued things, and there has to be enough room for the projectors to live. So you get this tensor product coming in. There would actually be, if you try to use the product of projectors, for a start you would get a problem that might not even be well defined, because they wouldn't necessarily commute. You can also think of this tensor product, again, if you think of the underlying non-local game, you got Alice Bob in the first corresponding to the first morphism, and another Alice 2 and Bob 2 for the second morphism, and everyone has to play. So where do they play? And you create sufficient resources that they can both play using the tensor product. So then the reason you get this d prime is just taking the dimension of the tensor product. I mean, that's how it arises. Of course, when you perform the specific measurements, you are, in some sense, destroying that part. Well, you know, if you think of it that way, destroying that part of the system. But that's exactly why you need separate resources for both sides to operate.
Okay, is there one more? Yes. Okay.
So if I understood you right, earlier you mentioned that in the quantum world you can color graphs using fewer colors than in the classical world.
Yes.
But I'm not really familiar with this field. So, but when I do a cursory search, a web search, what comes out is quantum algorithms to speed up classical graph colorability.
Well,
so
I
do you
mean,
have a link that I could read more about
it's
this?
a good. I mean, yeah. I mean, of course, you could say that. I mean, so in a sense, this is just yeah. I mean, there's a mathematical question that can you win this graph coloring game or whatever using quantum resources, and you get this different answer. So that is not the same thing as taking a classical algorithm, executing the same algorithm with the same inputs and outputs, but doing it faster. So it is a different kind of species of problem. So it's a different dimension of quantum advantage. Of course, we're interested in both, I think.
All right, thank you very much. I think in the interest of time, let's leave it there. If there are more questions, more discussions, you'll stick around, right?
Sure.
Cool. Yeah. Awesome. Let's thank Professor Abramsky one more time.